Today we'll look at 2.2, which is how plate tectonics form the ocean. There's a lot going on in this initial picture. You may want to refer back to it after we finish the notes here. All right, so back in 1912, Alfred Wegener proposed the idea that all the continents were once joined together in a supercontinent, which he named Pangaea. And his theory was known as continental drift, but it was not widely accepted at the time, so it really wasn't a theory back then, it was just a hypothesis. Then, about 30 years after he died, the how became better understood. So people, the reason they didn't believe his idea that the continents had spread around was that there was no way to show how that would have happened. There was no idea on how they would have spread apart. So when plate tectonics came along, it explained the how to Wegener's continental drift theory. So the main features of the plate tectonics theory is that the Earth is covered by a series of lithospheric plates. So think of the rafts in the pool that we mentioned earlier. That the ocean floors are constantly moving and spreading in the center, seafloor spreading, and sinking at the edges where they are subducting under continental crust and being regenerated. That convection currents in the mantle are what are moving the plates, and that heat is what drives the convection currents. So let's take a look. Here in the middle of the ocean, we have two oceanic crusts, and they are separating at the mid-ocean ridge. Now, that just happens to be where they're separating, and that would create cracks in the crust of the ocean called rifts. Well, when the rift occurs under water there with oceanic crust, which is thin, sometimes that releases pressure in the mantle, and magma is able to rise up and fill in the rift, creating new crust, new mountains. It's called the mid-ocean ridge. And so we find in the middle of the oceans these huge mountain ranges that travel through the ocean basins where the seafloor is spreading. So as this magma reaches the surface and solidifies to form new oceanic crust, it's called seafloor spreading. And that's what Robert Ballard went down to look for way, way, way back when he was a young man. Now, the mid-ocean ridges are actually chains of these like volcanic mountains rising up from the seafloor, and they are connected into these super long, the mountain range is actually quite long. It travels all the way down through the Atlantic Ocean and the Indian Ocean. There's some in the Pacific Ocean. Now, the lithosphere, which is the crust, and the little bit under the crust, is broken into a number of plates. There's about 20, and they're called lithospheric plates or tectonic plates. They can contain only continental crust, kind of like, you can't see it really well on this picture. Some of them contain just oceanic crust, like the Pacific plate in the middle there. And then most of them contain continental crust and oceanic crust, like the North American plate and the South American plate. And mid-ocean ridges form the edges of many of those plates. So when you look at this picture, the red line is the mid-Atlantic ridge running down through the middle of the Atlantic. And you see that they're also in the Indian and the Pacific Ocean. So here's a look at some of the major lithospheric plates. Which plate do we live on? We live on the North American plate. The next question says, what direction is it moving? So our plate is moving to the northwest. There's the arrow in the middle. What plate is moving away from us? Well, if you look over here in the Atlantic, the Eurasian plate is moving to the east, while the North American plate is moving to the west. And then lastly, which plate is pushing on the west coast of South America? So if we look at South America, you see that the Nazca plate is pushing against the South American plate along the western edge of the continent. And what you notice there is that word Andes. What does Andes stand for? Yeah, it stands for the Andes Mountains, and we'll come back to that in a minute. So here's a question, though. If plates are getting bigger, if the seafloor is spreading, is the Earth getting bigger? Well, actually no, because even though new lithosphere is being created where the seafloor is spreading, old lithosphere is being destroyed where the seafloor meets the continents. So if you look in this picture, to the right where the yellow arrows are under the word continent, you see that the oceanic crust is moving underneath the continent. And when it shifts underneath, and when it slides underneath, it's called subduction, but it begins to melt and become part of the mantle again. So it gets regenerated, I guess you could think of it that way. That also, where it dips down and begins to pull downward, forms trenches. You don't see them on this particular picture, but that's something good to remember. All right, so how much do the plates move? Well, the North American plate is moving to the northwest about 1 inch a year, whereas the Pacific plate is moving about 3 to 4 inches a year. So it just depends on the plate and how fast they're moving. My question is, what plate causes the earthquake activity in California? So if we look at California here, there's two things happening. There's the Juan de Fuca plate, which pushes against Washington and Oregon and Northern California. And then there's these two arrows that are side by side, showing that the plates don't push against each other like head on, but they rub past each other. And that rubbing there is what causes those earthquakes that California has. So, just to recap, because of seafloor spreading, the distance between Europe and North America is increasing by about 1 inch a year. So as the Americas have been carried farther away from Eurasia and Africa, we realize that the Atlantic Ocean means that it's getting bigger, whereas the Pacific Ocean continues to shrink. Now there's 3 types of plate boundaries. We're going to go over them quickly. The first one is convergent. This is when you have a collision of 2 plates. You have an oceanic and a continental plate. They come together. What you notice in the picture is that the oceanic plate is sliding under the continental plate. And that's what always happens. The oceanic slides under the continental because the oceanic is more dense. So it's a little bit heavier, if you want to think of it that way. So it slides under and yields to the continental plate. Now, one thing you notice is that as that oceanic plate, and in this case the Nazca plate, as it is sliding underneath the continental plate, it begins to melt. And when it melts, it creates magma. And some of that magma is able to find its way back up to the surface through cracks and openings, weak spots in the rock. And so that allows volcanoes to form. And actually that's how we think the Andes Mountains formed and continue to be shaped today by these volcanoes that are formed as the Nazca Plate and the South American Plate come together and the Nazca Plate subducts under. Now when an oceanic plate collides with a continent, like we said, it always descends down into the mantle, melting and becoming recycled. Now, what about when 2 oceanic plates come together? So if 2 oceanic plates come together, one of them will sink or subduct, and the other one could be making volcanoes. Because again, when the plate that is subducting begins to melt, magma that's now created is able to rise up through cracks and weak spots, and it could form volcanoes. And one example of that is the Aleutian Islands off of Alaska, that ring or that island arc. Those islands were created by volcanic activity in this very way. A lot of Alaskan mountains are actually, volcanoes. Okay. And in the last picture there, what was interesting about it, I asked you what marine tool that is, there was some seismic wave monitors attached to the bottom of the ocean. They're actually all over the world. And when they pick up some seismic activity, they send that information to the buoy. They're often connected to a buoy. They send that through the wires to the buoy. The buoy sends that message via satellite. The satellite then sends the information to the research station so they can look to see, do we need to post a warning, what's going on. So that was just an interesting demonstration of a type of marine tool that I wanted you to write down, the seismic wave monitor. Now let's go to two plates coming together, but this time they are both continental. So when two continental plates collide, there's no trench, there's not usually any volcanoes, because continents are very thick, so when they come together, they just push on each other and form mountains. The mountains, the rocks just fold and push upward, forming mountains like the Himalayas, for instance, which is the Indian plate pushing on the Asia plate. All right, that was all convergent, where two plates are coming together. Now we're going to look at a boundary where the plates are moving apart, which, if you remember, would be seafloor spreading. But it also can happen in some other places. When two oceanic plates pull apart, that makes a mid-ocean ridge. It's called seafloor spreading. But on land, when they pull apart, it just makes a big rift valley. There's one right here in Iceland. Just so happens that the North American plate and the Eurasian plate both have their boundary right through Iceland. So on land in Iceland, the boundary looks like this with a big rift valley. There's no magma that's able to reach up through there, though, because the continent's very thick. But right here, right where the plate boundary goes offshore, it looks like this. You can still see the crack. You can scuba dive in it. People do. It's kind of a neat thing to do. And that is the divergent plate boundary. So again, North America and Eurasian plates are pulling apart, creating this divergent boundary. Most of the area where that happens is the mid-ocean ridge there in the Atlantic, but it just so happens that since it goes right across Iceland, you can see the rift valley on land, and you can scuba dive in the crack or the rift. The third type of boundary is called a shear boundary, and shear boundaries form when two plates slide past each other, and they don't create or destroy any lithosphere, but they sure can make earthquakes. Because think about it, as they rub against each other, there's a lot of friction that builds up, and then they kind of lock together, and then finally when there's a little bit of a give, enough stress builds up that they slip, then that releases a tremendous amount of energy in the form of earthquakes. Where does this happen? Well, it happens right here in California. The plate boundary runs down there on the red line. You can see the red line. And that is where the two plates are sliding and slipping past each other. So that's why that area is prone to many earthquakes. So again, the three types of boundaries are here, coming together, pulling apart, or sliding past each other. And this I just wanted you to practice matching up an example. So convergent would be the one in the middle, which shows India pushing against Asia, forming the Himalayan mountain range. Divergent would be the one on the top, which shows the Great African Rift Valley, which is in Africa on the east coast. It's quite large. So the plates are pulling apart there. And then, of course, thirdly, the San Andreas Fault in California is a shear plate boundary where the plates are sliding past each other. All right, that's all we have for today. Thank you so much.